Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Stefan from Business Review, and I will be your host. It is our pleasure to have Smiths Interconnect with us today, who will be presenting this webinar titled, What are 5 Challenges RF Cable Assembly Face in the Space Industry? Today's guest speakers are Mike Carlson and Andrew Breslin. I'd like to welcome you to our webinar platform On24. You'll notice that this webinar is browser-based. So if you did disconnect for any reason, please just click on the link you received via email to rejoin the session. In order to ask questions, you can send them in via the questions widget. Just type them into the box at the top left-hand corner of your screen and click submit. We will allocate some time at the end of today's session to address any questions or thoughts that you may have. Please use the yellow help widget if you require any assistance, and keep in mind you can move, resize, and maximize any of the windows in front of you for a better view of the slides. Please note in the resource widget you will find today's presentation along with some additional helpful content to download. But for now, please allow me to hand over to Andrew.
Thank you, Stefan. I'm happy to talk with you all today, and also thank you, Mike, for your time.
Thanks, Andrew. I'm looking forward to addressing this topic around semi-rigid cables today, but first we'd like to open the conversation with a quick survey to the audience. Stefan, could you please launch a survey to get our results of the 5 challenges and see what percentages we come up with?
Absolutely. Today's polling question reads, which cable assembly challenge are you most concerned about for your space application? Radiation hardening, cable routing, modularity and multi-way housing, reliability and lower cost of ownership, shielding effectiveness. Is there any particular reason why you chose to ask this question?
Yes, Stefan. So we wanted to get a gauge from the audience in terms of where their interests lie and what challenges they've seen in their own space applications and from their standpoint. We will be covering all 5 topics today, but if one is more interesting to the audience than another, we may be able to spend a little bit more time on that particular item.
Perfect. Thank you. Now let's take a quick look at the results. So 55% of people voted reliability and lower cost of ownership, 22% of people voted radiation hardening, 5% of people voted shielding effectiveness, and 5% voted cable routing. Thank you.
That's excellent. So we will try to spend a little bit more time on a couple of the subjects that have some greater interest from our survey folks here, but for now we're going to jump into radiation hardening, and we'll get started with that topic, and we'll address all 5 in here shortly.
So on to radiation hardening. So one of the things that has been brought up by our customers and industry experts is the need for radiation hardened materials, and we see that 22% of the audience thought that to be the most important topic that is concerned to them. So when it comes to coaxial cables, what sort of materials are needed, Andy, in order to meet radiation requirements for space applications?
Well, Mike, it can depend on whether the application is going to be what we call inside the radiation blanket or outside of the radiation blanket. Outside of the blanket, applications are more exposed to radiation found in space up to the point that the environmental radiation can actually cause significant wear on the cable just by being in the environment. If you look at our diagram here, it's a rough sketch of where you find outside the radiation cables and versus inside the radiation blanket cables. So cables that are found inside or internal to the satellite are typically more protected already, and those that are being exposed to the space environment are what's called outside the radiation blanket. Typically the cables that are found outside the radiation blanket need to be rated for at least 100 megarads of higher total dosage, meaning that over the lifespan of the cable, the jacket can be exposed up to that amount with minimal degradation of materials and performances. Most of these cables are used between boxes and modules with the jackets exposed to the external environments. With semi-rigid cables, both the aluminum and copper-rated jackets or copper jackets are rated to meet or exceed this performance requirement.
So, Andy, is it safe to assume that cables inside the blanket require less radiation resistance?
Exactly. So cables inside the blanket are typically rated significantly less total dosage than the ones found outside of the blanket. Many of these cables are inside of boxes and therefore not exposed to external radiation. As a result, there's already some protection from exposure. These cables may need to be rated anywhere from about 10 megarads up to 100 megarads, but most are on the lower side of those requirements. Again, with the seamless metal tubing I use as an outer conductor on the semi-rigid cables, these make ideal cables for short run inside the boxes wherever radiation-resistant cables may be required.
So Andy, how does the wear material materialize? What is the impact on the cable and system performance?
Cables that are not made with radiation-resistant jackets will wear very quickly electrically, which causes the actual dielectric to start to break down and the cable significantly degrading in insertion loss performance. Once the insertion loss increases to the point of becoming less efficient and sometimes up to the point of no longer being able to pass signals at all through the cable, at this point, the entire RF signal is really disrupted as the antennas will no longer send or receive signal with the rest of the satellite.
So thank you for that, Andy. Hopefully we'll get more questions at the end of this session on radiation-hardened materials and what they may require for specific applications and what questions people may have. So our next topic is cable routing. So cable routing, another challenge that's been brought up has been cable routing within the system. Some of the concerns have been raised about how to best determine cable designs to be able to incorporate into the system. So Andy, could you bring up this topic?
Yeah, Mike, that's an excellent point. So routing can be a challenge for several reasons, including the types of bins that are required, the size of the bins required and the radius is needed, whether it's better or easier for customers to route it on site or to purchase the cables pre-bent. Most of these are going to be specific for their needs, depending on the actual satellite or system that's being designed, and can be handled in different ways. I'd like to point out that the copper jacketed cables are almost always purchased in bent configurations. This is due to the jacket thickness and the need for specialized tooling in order to bend the cable without damaging it. There are minimum bend radii that require this tooling in order to prevent damage to the jacket, which can happen if the cables are bent too tightly or if they're bent and unbent while trying to get them into the final configurations.
So Andy, is there any other sort of routing options that are available, and what do customers don't have need for tight bend radius or they have specialized tooling needs?
Yeah, of course. So the other option for semi-rigid cables is to use an aluminum jacketed cable, which are much softer and can be bent by hand. This type of cable can be sold in straight lengths, or if in longer lengths, they can be sold as lightly coiled in the packaging. There are still things to consider when bending this type of cable, but if customers uses wide radii, the cables can be typically bent by hand to their specific routing needs.
Thank you, Andy. So Andy, what are some of the advantages and disadvantages of straight cables versus preformed cables?
So one of the advantages of the straight cable or the loosely coiled cables is the cost of acquisition, including shipments. In some cases, depending on the exact bending specifications and packaging requirements, it can be a significant savings over bent cables. The disadvantage of this approach is that the cables will still need to be bent on site in order to install them. If you look at some of the images on the current slide here on both the left and the right images, these are pictures of actual cables installed on a satellite that a customer's routed themselves. And you can see some of the cable management systems they've used and some of the wider bend radiuses that they've bent by hand. The disadvantage of this approach is that the cables will still need to be bent on site. If the installer doesn't know how to properly do this without damaging the cables, it can significantly increase the cost as there may be a need for replacement cables. Schedule delays can also occur as oftentimes purchasing a new cable assembly may need to wait for manufacturer's lead time if the cables are damaged from not bending them properly. However, if done properly, there shouldn't be most of these major problems, but it does add some risk to the satellite build. And as satellite manufacturers know, major schedule delays often come with significant fines from their customers. Some of the advantage of the bent cables are typically that the cable assemblies come to the customer ready for installation. This is reduced risk for the customer and can improve installation times for them.
Thank you, Andy. That was great on cable routing, and hopefully we'll get some Q&A at the end on cable routing and some concerns people have. The other topic we'd like to cover of the 5 ways is modularity. So one of the main challenges facing satellite manufacturers today, in today's world, is the lowering the cost of installation of cable routing within the satellite payload or ground station network. One of the ways in which people are solving this issue is creating quick disconnect modular multi-way coaxial connectors, housing up to 16 semi-rigid cables into a single housing. A lot of these have very low VSWR, the spring-loaded SMP style and SMPM style coaxial contacts that can be mounted in multi-way housings, allowing for extremely low VSWR, up to 40 gigahertz, low insertion loss, and precision phase matching. In this manner, cumbersome SMA threaded single-way connectors that requires precise torquing and time-consuming inspection within the RF payload can be eliminated within a single multi-way housing, solving this issue and greatly reducing the time of installation without compromising the electrical high-frequency performance of the system.
Mike, you mentioned that the installation could be faster. I'm just curious how much faster. So we've had some customers tell us it can take up to about 9 minutes per SMA to install and inspect the connectors. Would this be about the same for one of these 16-way type harnesses?
Yeah, Andy, we estimate that it would take approximately 3 minutes to install a quick disconnect connector with quick latch hardware with quarter turn with up to 16 coaxial contacts into a single-way housing. We're showing here a 2-way housing on the screen with quick disconnect hardware. So this can be mounted with SMP or SMPM coaxial contacts that are spring-loaded, allowing for that extremely low VSWR and insertion loss. And we can put this into 2, 4, 8, and 16-way housings. And we offer that with a micro D or a D sub type format. So if there are any other questions about that, we certainly can offer and provide additional data.
Thanks, Mike. That sounds like a great way to solve a lot of these production problems that we've heard about, especially as the number of small sats in production continues to increase. This type of connector should be able to help a lot of manufacturers increase their throughput and keep on their schedules.
Yes, Andy, thank you very much for that. There certainly is a lot of things that can be done with modularity and a lot of different formats, and customization is possible with that. And certainly we'd like to move on with the other things that can be done with that. And if there's anything else that you'd like to cover with modularity, Andy?
At this point, I think that's going to wrap us up in the modularity section, but I think we can move on to probably our highest survey total results here, the high reliability solutions and lower cost of ownership.
Great. Okay, I'll move on to that. So next topic is high reliability solutions with lower cost of ownership. So one of the things we hear about all the time is the idea of lower cost of ownership. Andy, how does that translate to high reliability semi-rigid cable assemblies?
So this can come out in several different ways, Mike. When we talk about the lower cost of ownership, we're not necessarily talking about the lowest pricing, but other factors that fall into that are the durability of the product, the reputation and trustworthiness of the supplier, if parts are providing a value to the user greater than the competition or the competitive products. Some considerations may be that if phase stability is needed and a supplier only offers standard PTFE dielectrics. And for those that don't know, PTFE is a material called polytetrafluoroethylene, and it's a very common material used for electronic insulators. Low-density PTFE or other dielectrics can offer better phase stability over temperature that's often needed in space environments. Another thing not considered in most applications, but is critical for space applications, is proven heritage of supplying S-level assemblies. If a supplier is not experienced in these types of applications, important details can be missed on in contract reviews, quality documentation, and specification requirements. Suppliers that have a history of supplying parts into space applications are significantly more prepared to manage those type of requirements, thus reducing the supplier risk and potential costs. Qualifications done by the manufacturer can also reduce the overall costs. As most customers want specific test plans, most of this data can't be shared with other customers, and as a result, they have to redo testing when they purchase assemblies for the first time. If the manufacturer performs testing of their own and has their own qualification reports, they can often incorporate not only industry standards, but also more stringent testing to show the limits of the product. In many cases, this testing will overlap with the customer's needs and thus reduce the amount of testing needed to be done for qualifications of future assemblies, further reducing overall costs.
Great, Andy. One of the topics you also mentioned was need for phase stability. Can you elaborate on that, please?
Yeah, Mike. So depending on the orbit a satellite may take around the Earth, it can see periods of time where it's exposed to sunlight for a long period of time, and then other periods where it's exposed to darkness for several hours. And in either case, those can result in some temperature extremes, where in the sunlight it can be very warm, and in the darkness, obviously, very cold. For many of the mechanical systems on board, this typically isn't a huge problem as long as the materials they are made from can withstand the temperature cycling. But in an RF path, these temperature swings can actually lengthen or shorten the electrical length of the assemblies or the electrical length in the path. This causes issues with signal timing when signals are being combined via multiplexer, as they are in many of these circuits. There's a need to keep consistency in the signal timing. The greater the overall deviation that a cable can change in this path, the greater the probability that the electrical lengths of multiple cables may be different. By using dielectric materials that offer greater phase stability overall, there is a significantly smaller window of overall deviation, and as a result, much higher probabilities that the signals will remain consistent. This is also why cables with this need often be purchased as phase matched, meaning that nominal electrical length of cables will be very close to each other, so that as the cables do change with temperature swings, the electrical lengths will remain more in sync with each other.
So, Andy, is there anything else that you'd like to say on the lower cost of installation and high reliability solutions at this point in time?
Well, certainly, like I said, it does benefit a satellite manufacturer to go with sources that are already qualified and already have some of the materials that they can offer in terms of the test reports and the knowledge that goes with some of those S-level type of assemblies. But in general, today, I think that covers most of what we wanted to mention in terms of the high reliability solutions. I certainly would be happy to answer any questions that come up around that subject if we didn't address those topics in the call here.
Certainly. Thank you, Andy. So another topic we'd like to talk about is shielding effectiveness. This is the last topic we need to discuss. This is shielding effectiveness of the cables and the benefits of the shielding. How do the semi-rigid cables stack up regarding the shielding effectiveness topic, Andy? And can you please cover some of these points that are very important?
Yeah, Mike, of course. So it's actually a pretty strong case for the semi-rigid cables, is the shielding effectiveness of those cables. All semi-rigid cables are designed with a seamless metal tube as a jacket, and as such, they have much greater shielding than the flexible cable assemblies. Both copper and aluminum jacketed cables have greater than 100 dB of shielding effectiveness, which means that the very minimal RF signal gets outside of the jacket, and therefore minimal cable crosstalk can occur. If you look at our diagram here, you can see three cables very closely together in a system, if they were installed, and where they're that close and there's cable, RF signal leaking, it can be picked up by another cable and cause distortions in the signal itself. Also, another thing to mention here is the different types of shielding layers. So in a standard MIL-DTL-17 flexible type cable, you often have a single layer of braided shielding, it creates about 60 dB of shielding effectiveness. In most of the higher end, low loss type of cables, where you have a multi-layer braided cable, you get about 90 dB of shielding effectiveness. But with both the aluminum or copper jacketed semi-rigid type of cable, you have greater than 100 dB of shielding effectiveness. And it's one of the reasons that they're often chosen in those type of applications. The shielding effectiveness will help protect the signal integrity when many cables are running side by side next to each other, as the RF leakage out of one cable may be picked up by another, and like I said, it creates some distortions in that signal. As satellites will have limited physical space to spread cables around, and out, they're often routed very closely together. As a result, it is important that many of these situations have a high level of shielding.
Great, Andy. Is this frequency dependent, the crosstalk and the shielding effectiveness? Or is there a graph that shows shielding effectiveness over frequency?
We don't have any graphs in our presentation today, but certainly the higher the frequency in an application, the lower the cable will have shielding effectiveness, meaning that the faster the signal is running in the cable, the more likely that it can actually leak out of the cable. At lower frequencies, you'll often get better shielding effectiveness out of a cable. Most cables are rated either between 1 gigahertz, because that's where it can be measured easier, or at 18 gigahertz. But there is a correlation between the frequency and the shielding effectiveness itself. So the greater the frequency, the less effective the shielding will actually hold the signal in the cable.
So most of the cables that you mentioned in the shielding effectiveness on this sheet here is up to 18 gigahertz and beyond.
Correct. Well, yes and no. So the three at the bottom there, yes, they can all reach 18 gigahertz or over. The MIL-DTL-17, it's sort of a mixed bag. Most of them are designed for lower frequency military applications.
Great. So, Andy, could you now elaborate on the difference between flexible and semi-rigid cables when it comes to shielding effectiveness for the audience?
Sure, Mike. So you see here, this is on the screen is an example of a flexible cable, and you can see on the right-hand side where the braided layer actually is in the cable underneath the jacket. Flexible cables have that braided layer and some layered shielding underneath those outer jackets. And the basic structure, something like that MIL-DTL-17 or an RG type of cable, this is usually one layer of braided outer shielding. In many of the higher end cables that we talked about, you'll find 2 or 3 layers of braiding. This type of shielding is made up of really thin wires braided together around the dielectric cables or around dielectric materials of the cable. In some cases, there will also be a metallic wrapped or served layer as well. This type of shielding works very well in flexible applications because it allows the cables to maintain multiple flexures without damage to the layers. The downsides, unfortunately, come that the shielding effectiveness of this approach are not quite as good as that solid outer tube that the stainless or that the rigid cables come with. Because those layers are braided, there's even small gaps between the wires where RF signal can pass through, and even when they're overlapped with several layers, there's still some gaps. But as you would expect with that approach, this type of shielding usually results in between about 60 and 100 dBs of shielding, like we talked about in the previous slide. Based on the frequency in use, of course. The number of shielding layers and the type of shielding patterns used also will affect this. The semi-rigid cables, however, use a seamless metal tube for an outer shield and have no large gaps where RF signal can easily leak out of the cable, and therefore have a result of about greater than 100 dB of shielding for most of those type of cables.
Great conversation, Andy. I really appreciate that, and hopefully we have some questions on shielding effectiveness that we can answer at the end during the Q&A session. We'll now move on to the conclusion of this presentation and then go on to the Q&A session, then follow on with a further conclusion.
Yeah, so in conclusion, we just wanted to mention that Smith's Interconnect product portfolio offers solutions to all the above mentioned challenges. Some of our cable assembly products are capable of meeting up to about 750 megarad of total dosage of radiation with minimal or no radiation degradation over the extended life in the space environment. Our semi-rigid cables are sold in both straight and unbent configurations, and also can offer a full range of flexible cable assemblies to help with your routing and your projects. Our multi-way connector, coaxial connector assemblies are offered in both SMP and SMP-M size contact interfaces, and from 2 to 16-way connector housings with either quick latch hardware or the standard latching hardware to enable a more modular assembly that can significantly reduce some of that installation time. These connectors are designed for high-frequency operation and low BSWR. We offer both flexible and semi-rigid assemblies with high levels of shielding effectiveness. Smith's interconnect cables have flown on over 40 flight programs with over 20 plus years of experience and over 100,000 assemblies in space currently, where we are extremely familiar with that space level requirements and the specifications, and can design and manufacture assemblies to meet or exceed both customer and industry requirements. We offer several standardized test plans as well as custom test plans if needed, and can supply qualification reports for our flight qualified cables, including our Space Next Q series of flexible cable assemblies, which was designed to have pre-qualifications and standard testing available for our customers.
Thank you for that, Andy. Now we'll move on to the Q&A session, and we'll go ahead and hope to answer those. And I think go ahead and Stefan, could you start off with that, with Andy answering some of the first questions?
Yes, absolutely. Thank you. So it is now time for our Q&A session. Just a reminder for the audience, in order to ask questions, you can submit them in the Q&A inbox. Just type them into the box and click submit. But we have some questions coming in already. Our first question for today is, are your cables MIL DTL17 qualified?
So, Stefan, some of our cables are MIL DTL17 qualified. They're either purchased to that specification, especially in an RG type cable. When it comes to semi-rigid cables, you're looking at things like the RG405 or the RG402, which are just different sizes of copper-jacketed MIL standard cable assemblies. We also may have a line of flexible assemblies, which are all designed to either meet or exceed all of the requirements in the MIL DTL17 standards. So while our cables are not all made to that MIL spec, they all can either pass the testing or they already are qualified to that testing. And if customers need actual test results, we can do that. We can perform that testing on our site here as well.
Thank you very much for that answer. Our next question for today is there a standard or preferred semi-rigid cable size for space applications?
There is not a standard. Well, there are standard sizes. There's not necessarily one that we would say this is the right one for space applications. Most of those considerations are going to go into things like a insertion loss needed, the power needed in an application, the frequency needed. Those are going to vary depending on the size of cable. And so the smaller cable that's used can typically reach higher frequency ranges. They have greater insertion loss, and they can handle less power. But as you move to larger cable sizes, you're going to be able to handle more power with those cables, and the end result is that the cable won't work to certain frequencies depending on the cable itself, how high you can get. So that's really going to result. It's really going to matter what the customer's using it for and what they need in their applications.
Thank you very much for that answer. Our next question for today is, what is the impact of poorly routed cables or bent cables from a customer perspective during build, launch, and operation?
Yeah, so during the build is typically where you're going to see the poorly routed or bent cables from a customer's perspective. So those issues are going to result in things like schedule delays potentially, or having to repurchase cables if they are broken during installation. Usually once the satellites, everything is installed in a satellite, the systems get tested pretty thoroughly before they go into flight. So you won't often have problems after the initial build phases. But potentially if there was an issue and a cable did launch the satellite and it was damaged or had some underlying issues that weren't seen necessarily during the test phases, it would be critical damage to the satellite. So basically, once a cable gets damaged, no signal is going to be able to get through it, and that result, you won't be able to actually communicate with that satellite. The RF signal from the antennas and to the systems would no longer pass to the cable. So it is important to make sure that the cables are routed correctly and are bent correctly before installation, in order to reduce any kind of risk in terms of those issues later on.
Thank you very much for that answer. And just a quick reminder to the audience, you can still send your questions via the Q&A widget. But moving on to our next question for today. Is the shielding effectiveness per analysis or testing?
It depends on the actual cable. So Smiths offers, I don't know exactly the number, something around 70 different cables in total. Some of them have been tested, and other ones are designed per analysis. So if we know that, as an example, a seamless copper jacket is going to result in greater than 100 dB of shielding, we know for pretty well that all the copper jackets are going to be the same. But certainly when it comes to flexible cables, most of those are by manufacturer ratings, which is typically done either originally from qualification and testing, but then later from an analysis standpoint.
Thank you very much for that answer. Our next question for today is, are the quick disconnect connectors keyed?
Yes, I can answer that. The quick disconnect connectors are keyed in that you can have a wedge shape or a six-way hexagonal type mating with the quick lock hardware or the threaded hardware, so you can put that into 36 different locking positions. So there's many different formats we can do, but many of those are keystone shapes, so you can ensure that you cannot put those in backwards or upside down.
Thank you very much for that answer. And our next question for today is about the connectors any being used by ESA and with ESA approval.
Yes, we do a lot with ESA. Certainly there's a lot of different test reports that we have, and we have many of the primes that do that. And we do work with ESA on many of the connectors that we provide.
Thank you very much for that answer. Our next question for today is, you said the connectors are capable up to 40 GHz. What is their optimal range?
Andy, do you want to answer that?
So, I mean, depending on the type of connector, we have a number of mil standard 348 connectors that work pretty well through the desired frequency range. You know, SMA, as an example, work to 26 gigahertz, type N to 18, et cetera, et cetera. When you look at our multi-way housing connectors, I think the range of operation is DC to 40, and I believe it tests pretty evenly through that frequency range. And Mike, you may know a little bit about that as well, but I believe they work optimally up to 40 gigahertz. I think yes.
On the multi-way housings, we get 40 gigahertz with a mated VSWR below 1.25 to 1, and very low insertion loss depending on the cable type that you choose. And certainly the larger diameter of the cable, the lower insertion loss you'll get. On smaller cables, we recommend the SMPM interface. On larger cables, we recommend the SMP interface to get the larger cables into the backside of the connector and to offer the lower insertion loss if needed over higher frequency or higher cable lengths as needed.
Thank you very much for that answer. And again, a quick reminder to the audience, you can still submit your questions via the Q&A widget. But moving on to the next question, are copper alloys used for shielding?
So the cables that we use are typically based with copper, and then there's a plating over that, and the plating could be either it could bear copper or it could use a tin plated or silver plated, depending on the application. Usually for space, we avoid the tin plated option, but in other applications, it is used frequently. And so that seamless tube is really just a copper tube around the dielectric of the cable, and yes, it is used for shielding. So in any of the semi-rigid cables with that seamless tube construction, you can get greater than 100 dBs of shielding and really eliminate the crosstalk between assemblies.
Thank you very much for that answer. Our next question for today is, what is the best, most efficient way for customers to specify pre-bent semi-rigid cable geometry? Okay,
so there's a couple of ways that customers can make it easy for both the manufacturer and themselves when designing a bent semi-rigid cable. Some of those things are going to be oftentimes overlooked, but it does really ease the process. And so some of those things are making sure that the bend radius is the largest that the customer can allow for. meaning that if the smallest size that they have available in their system is the minimum bin radius, then that would be probably what needs to be specified. But in often cases, they'll write the minimum bin radius down when really they just need, a bend around a corner or something. There's not a lot of tight spacing, in that area. Another thing that can be looked at whenever possible, it's easier to do 90-degree bends as opposed to an odd angle of a bend. When you use some of the automated equipment, it's not too bad, but if any of the, especially on some of the smaller volume type applications that are sometimes found in the space industry, some of those are done by hand, and so 90-degree bends are typically easier to calculate and measure when done by hand. Another thing that can be done very simply that most customers don't think about is using the same bend radii as often as possible. And so if like I said, that minimum bend is needed, or the maximum bend that they can go with is a 1/4 inch, try to use a 1/4 inch everywhere as an example in an application if the cable allows for it. That way, manufacturers aren't changing their tooling when they're bending the cable. It makes it go a lot simpler and easier with their equipment as well. So those are 3 things that customers can do when designing their own bent semi-rigids that make it much easier, both from a design standpoint as well as a manufacturability standpoint.
Thank you very much for that answer. Our next question for today is, how are tin whiskers dealt with on the aluminum semi-rigid cables since they're tin-plated?
So a couple of things on the aluminum semi-rigid. We do have a tin-plated version of that cable. Typically, those aren't used in space. And so what we go with the space industry is typically a silver-plated cable, which eliminate the tin on the outside in terms of the plating. And then in terms of all the soldering as well, we use a standard solder, not any of the Rojas solders from most space applications, to reduce the amount of tin in the assembly at all. We try to make sure that tin plating isn't going to become an issue with our customer base. It is things that we need to look out for. And so it's important to know the applications up front when we're looking at the cable assembly. So when we're designing assembly with a customer, if we know it's for a space application, we'll typically recommend options that are not heavily involved or rely upon the tin materials.
Thank you very much for that answer. And again, just a quick reminder to the audience, you can still send your questions via the Q&A widget. And additionally, you can find the presentation slides at the bottom right-hand corner of your screen in the resource list. But moving on to our next question. Are semi-rigid cables sometimes ordered preformed per customer specification?
Yeah, that's quite often the case. We do, obviously we do offer the straight or lightly coiled options, but frequently customers do need bent cables delivered to them. So they'll send us a specification and we'll review it, provide any notes or feedback that is needed to the customer. And then at that point, once we agree on the specifications required, go about with a quote or an order or whatever the next steps are there. Some of the things that can be done are some of the things that we need to look out for in some cases are, although the manufacturing assembly is usually relatively straightforward, sometimes the hidden costs of packaging and things of that nature are reasons that we may recommend a straight cable as opposed to a bent cable. And so it depends on how many the customer needs to buy, and again, what types of bends are needed, those bend radii and those sorts of things. But it is something that does come up common, and we can handle that pretty easily. But it does sometimes become more expensive because of packaging and things like that. A lot of those bent semi-rigids need to be custom packaged, which then, in order to make sure that none of the bends get bent any more or less during transportation, and in some cases that adds additional cost.
Thank you very much for that answer. Our next question for today is, are there situations where the flexible space NXT would be a better solution and would be used versus semi-rigid?
Yes, there are situations where a flexible might be a better solution. The semi-rigid cables, we primarily talked about those today because of the large number of benefits that they offer in space industry. However, there are flexible options that are quite good as well. And so one of those is what we call our Space Next Q and QT series product offering. And basically the Q is a low loss cable assembly line that's all made with ETFE jackets, low loss dielectrics for excellent electrical performances. We offer those in a wide range of different, or with a wide range of different standard connector interfaces, as well as some of our unique modular type connectors or multi-way housings. And then the QT series is similar in terms of insertion loss as our Q series, or comparable, I guess, because they are different sizes of cables. But one of the reasons you would use a QT cable is really if you need a really excellent phase stability over temperature. As we talked about, it is a need in many of the satellite applications, and the QT series was designed both to meet the requirements of the space environments as well as the phase stability needed in many of those applications. It's quite a popular product, and it is sometimes more or sometimes beneficial to go with one of those series as opposed to a semi-rigid. It really just going to depend on the geometries that the customer needs to install the cables. There are some cases where the space nets, because of bend radiuses and things like that, they may not be the best solution. But in other cases, it very well likely could be.
Thank you very much for that answer. And our next question for today is, do we simply meet or exceed the MRAD requirements? How high can we go?
Yeah, so the mega requirements in space are really because of the environment itself. We've tested cables from 30 megarads, in some cases, depending on the grade of the ETFE materials, 30 megarads. We have cables tested to 100 megarads total dosage. And then we also have some cables, and it's really these semi-rigid cables that we spoke about today, that have been tested up to 750 megarads total dosage. So really quite in excess of what's needed in most applications. But again, in the heavy dosage of radiation that a cable could see over a long lifetime in space, especially for many of the geo satellite applications, it will meet or exceed all the requirements in that environment.
Thank you very much. I'm afraid that's all the time we have for today. Just a reminder, if you didn't get your question answered today, a Smiths Interconnect colleague will follow up with you shortly via email. So that just leaves me to thank Andrew and Mike for what was a great presentation, and to Smiths Interconnect for sponsoring this session. Also, please feel free to fill out the survey located in the survey widget at the bottom of your screen, and remember that additional semi-rigid cable support documentation can be located in the resource widget alongside the PowerPoint slides from this session. To the attendees, you receive an email shortly telling you how to access the on-demand version of this webinar. You can access this on the Smiths Interconnect website at smithsinterconnect.com or our website, which is www.business-review-webinars.com. We look forward to sharing more webinars with you, so please keep an eye out on the websites just mentioned and follow us on Twitter at BRWebinars for daily updates. Thank you once again, and I hope you have a nice day.